All right, our topic today is the accuracy of measuring instruments. And we need to talk a little bit about what we're involved in here. Let me ask you this question to think about for just a second. If I measure something, am I ever perfectly accurate in doing that? Let's say, for sake of discussion, that I measured a board, and I said to you that board is 68 centimeters long. Now, is it very likely that that board is in fact exactly 68 centimeters long? Probably not. It's probably just a little over, maybe a little under, something like that. But we say it's about 68 centimeters. It is, in fact, 68 centimeters to the nearest centimeter. Now, you may wonder why this is really important. Let's think about this. Let's say that I were watching a swimming carnival, for example, and I wanted to time the swimmers. And so I pulled out my wristwatch, which has a second hand on it, and I timed the swimmers with my second hand. Is that going to be helpful? Well, it might, but probably not, because I'm probably going to have two swimmers that finish very closely together, within perhaps a few tenths or even hundredths or even thousandths of a second. You may remember that a few years ago there was an Olympic race between the American relay team and the Australian relay team, and that entire race, four-man relay, was decided by 1/1000th of a second. If the timekeeper was just using his wristwatch, that would not have been accurate or not enough. Another thing you might think about, those are sort of small-scale examples, but when we think about something like the size of the universe, and we talk about how far we are away, say, for example, from the sun. We talk about the fact that the Earth is 93 million miles away from the sun. It's just sort of a number that we use. It's pretty accurate, but are we ever 93 million miles away from the sun? Probably not, probably very rarely. We move back and forth depending on what season it is, depending on what altitude you're at, depending on what latitude you're at. Okay? We're talking about 93 million miles to the nearest million miles. It's just the closest estimate that we can get. Anything that we do in terms of measurement usually takes that into account. So our concept that we're actually dealing with today is called limits of accuracy. Now let's go back to our board for just a second. Let's say, for sake of discussion, that I have a board, and I've measured that board, and when I measure it, I come up with this measurement, 67.75 centimeters. Now when I round that off, you all know how to round, when I round that off, what does it become to the nearest centimeter? It becomes roughly 68 centimeters. What about if I measure the board and I come up with 67.5 centimeters? What does that become? It becomes 68 centimeters, because I'm rounding to the nearest centimeter. What about if I measure the board and it comes out to 68.4 centimeters? Now I'm going to round down, right? I'm going to round backwards because it's not 5 or more over here. I'm going to round down, and it's still going to be 68 centimeters. How about this? How about 68.49 centimeters? Now be careful. Some of you are going to say, well, that's a 9, so I round that to a 5 and then I round it up. No. When you're reading this measurement, you read the whole thing and you round by that. You don't round it one digit at a time. So what would this round to? This would round to 68 centimeters. Okay? Now what if I had 68.4999, so I can measure to 1/10,000th of a centimeter? What's that going to round to? It's still going to round to 68. So when we're talking about the limits of accuracy, the way we do this is we figure out what the smallest increment that we're going to measure is. You notice that we can go all the way down to a half a centimeter less than 68, and all the way up to nearly not quite, but nearly a half a centimeter more than 68. Right? So what we do in order to figure out limits of accuracy is we take our measurement and we add half of the smallest measurement, smallest increment of measurement that we're using. What's our increment of measurement here? It's 1 centimeter. So half of that, 1/2 of that, equals 0.5 centimeters. And what that means is then we add or subtract that from our measurement. So we say our measurement plus or minus 1/2 of the smallest increment. Okay, so for example, in this measurement, we would say 68 centimeters plus or minus 0.5 centimeters. Now, our term that we use is to talk about this is upper and lower bounds. So related to this is upper and lower bounds. Lower bound, subtract. Right? This is plus or minus. So we subtract. Lower is the measurement plus minus 0.5, and the upper is the measurement plus 0.5. Now, as you know, if we're completely accurate, we would say, well, 68.5, that'd be plus 5. They actually round up. But in terms of talking about the bounds, we go ahead and include that, even though we realize that exact amount isn't quite there. So, let me give you some examples of this. I measured something and it came out to 72 centimeters. What are the limits of accuracy? Well, our smallest increment here is 1 centimeter. Half of that is 0.5 centimeters. So we would say 72 plus or minus 0.5 centimeters. That is our limits of accuracy. Now, if we had this number like this, 86.6 millimeters, our smallest increment is no longer 1 millimeter, or 1 centimeter if I looked at centimeters. It's now 0.1 millimeters in this case. So I have to add 0.05. So half, right? 0.1. That's my measurement increment, our smallest increment, millimeter. Half of that would be 0.05 millimeters. So my limits of accuracy for this number would be 86.6 plus or minus 0.05 millimeters. Now, be careful what you're looking at. If we said this, 72.0 centimeters, that number looks the same as that one, but this is not measured to the nearest centimeter. It's measured to the nearest 1/10 of a centimeter. So again, our limits of accuracy for this would be 72.0 plus or minus 0.05 centimeters. Now, let's use a practical example of this. Let's say, for sake of discussion, that we have a square. As you know, I'm not an art teacher, but let's assume this is a square. And let's assume, for sake of discussion, that we have measured the side of our square and we have come up with 6 centimeters. And now I have 3 questions. The first question is, what are the upper and lower bounds of the sides of this square? Well, my smallest increment is what? 1 centimeter. And so that means, that means that half of that would be 0.5 centimeters. So we have 6 plus or minus 0.5 centimeters. So if I want the upper and the lower bounds, then I'm going to have 6 minus 0.05 is going to give me 5.5 centimeters to 6.5 centimeters. That is the upper and lower bounds of the sides of that square. Now what if I said, I want to know then the upper and lower bounds of the perimeter of the square? Well, the perimeter of the square is the 4 sides added together. So how would I get the lower and upper bounds? I'd multiply by 4. So if I multiply this by 4, I get 0, 2, 2, and I get 22.0 centimeters. That's the lower bound. Times 4 would give me 0, 2, 6. And that is the upper bounds of the perimeter. The lower bounds, the upper bounds. What if I wanted the upper and lower bounds of the area? How do I get the area of the square? Well, I multiply a side times a side. It'd be easy to say 6 times 6 is 36, plus or minus a half, and we're there. But that wouldn't be right, because this is my lower bound of a side, this is my upper bound of a side. So I need to say 5.5 times 5.5. That's going to give me the lower bound of the square. 5 5 is 25, 7, 2, 5, 7, 2, 0, 5, 2, 0, 30. 30.25 is the lower bound. The upper bound is going to be 6.5 times 6.5, which gives me 5, 2, 3, 0, and then 30. Carry the 3, 36 is 39, 5, 2, 2, 4. So my lower bound is 30.25, my upper bound is 42.25. And that is the accuracy of measuring instruments.